Hey everyone, welcome to another review video for Algebra 2, Module 3, Topic 2. Normally we do larger module tests, but in this case, just to wrap it up before spring break, we're going to do a shorter test on just Topic 2. And so I'm going to cover some questions about that here today. What you're going to need is your review sheet, or at least a way to take notes. And then probably Desmos, either the scientific or the graphing calculator. I have both right here ready to go because we're going to have to plug some stuff in and we're going to have to graph some stuff. Okay, so here we go. You can also use Desmos on the test, and then obviously you can use these notes on the test as well. All right, cool. So starting off, the first thing we talked about in this unit was just some different applications of exponential functions and how we use them in real life. One of those examples is the half-life of a substance. And so I give you the equation right here, which you kind of have to change around a little bit depending on the scenario. But let me tell you what each thing means. So A of t is just the amount, the left side. So you're going to be solving for that all the time. It's just a function. So really what you have to worry about is P to start, this big P. That is your starting amount. It's the number that isn't raised to a power, just hanging out in front. In the next two questions, it'll also be the starting amount. We might use a different letter for it though. The 1/2 that's in parentheses, that comes from the half-life, right? We're multiplying by a half because half is decaying. Remember, the half-life of a substance is how long it takes for half of it to go away, either in a bloodstream or just the mass of something decaying. And then in the exponent up top, we have the t variable, which is time. You can choose what time to measure in. So if it's hours or days or seconds, whatever the situation calls for. And then the n is the half-life time. How long it takes for something to decay. Okay, so we're dividing by that. If we multiplied by it, like we saw in an earlier example about coffee in the bloodstream in the book, you're actually making more than 1 half-life per hour. So we have to divide to make things slower, right? So in this case, in problem number 1, they want us to write the function if we have this table and then use it to figure out how much is left in the bloodstream after 32 hours. So here's the function. It's always going to start off with A of t, just amount with respect to time, equals my starting amount, which I can see from my table is 400 milligrams. So we'll just put 400. And then times 1/2 to the power of t, I don't know t yet, I'll just leave it as t, divided by the half-life time. Like how long does it take for 1 half-life cycle to occur? I have to get that from the table. If I look on the bottom, it tells me how many half-life cycles have happened. And then on the top, it's telling me the elapsed time. So after 1 cycle, I've lost half my amount, and that happens over 4 hours. Next up, 4 to 8 is the, well, this should be 2. The second half-life cycle, and then 3 after another 4 hours. So I'm going to guess that the half-life is 4. So 4 hours. So this is my equation, 400 times 1/2 to the power of t divided by 4. Okay. If I want the answer for 32, well, then all I have to do is set t equal to 32 and plug that in. So let me get Desmos up, the scientific version, because we're going to go scientifically. I'm going to just type in 400 times 1/2 to the power of 32 divided by 4. Oops. Which is 8. So in this example, we can say that there's 8 half-life cycles that have happened, and what's left over is 1.5625. 1.5625. So that is our answer. And that's what we're going to put in here. We have 1.5625 mgs, milligrams, and that's after 8 cycles. Okay. Here's another example. The half-life of phosphorus 32 is 14.3 days. Okay. If the initial mass of the sample is 4 kilogram, how much will remain after 365 days? Round if necessary. Okay, so let's set up our function once again. In this case, it's A of t equals, my initial sample is 4 kilograms. my ratio, what I'm multiplying by, is a half because I'm decaying by a half. And then this time, I'm just going to set t to be equal to time in days. And the last one, time was in hours. In this case, it's going to be in days. And so what I'm going to do is in the exponent, set it equal to t over 14.3. Okay. So if I want the amount after 365 days, well, then all that happens is the t variable in my equation turns into 365, and I'm still dividing that by 14.3, basically saying how many half-life cycles have occurred, how many times am I multiplying by a half, and let's go back to Desmos. So in this case, our starting amount is 4 kilograms. Our exponent is 365 divided by 14.3, which is very, very small. Now, I don't know if they want us to convert to milligrams or something. I guess we could, but my answer is 8.28 times 10 to the negative 8th. Remember, kilogram is 1,000 grams, so you could move your decimal place 3 to the right to go to grams, and then a milligram is 1,000, or there's 1,000 milligrams in a gram, and so really, I think it would be a bunch of milligrams, like 8 milligrams or something. But in this case, we'll just leave it in kilograms. So we'll say 8.2875, because that's the 1,000th place. Although the next number in the sequence is 7, so let's round that 5 up to 6, times 10 to the negative 8th kilograms. That's a really small amount, right? It started with 4 kilograms. This is a really, really small number, times 10 to the negative 8. That's moving this decimal place 8 times to the left, right? Which I think at the same time, if I converted that to milligrams, would also move it right 8 times. So this answer in milligrams is the same without the scientific notation, if that makes sense. But I would just leave it in scientific notation. That's all good. All right. Next up, we are given some extra stuff or some different stuff, and we want to figure out what the starting amount was. Okay, so in this case, CS137 has a half-life of 30.2 years. After 432 years, 0.0046 or 48 kilograms remain. What was the original mass of the sample? Okay, so this time we don't know P. I don't know what P is, right? So I'm still going to solve for the amount, except for I know what the amount is now. The A of T, the left side, is 0.0048 equals P times 1/2 to the power of 432, the time variable T, divided by the cycles, the number of half-life, or how long it takes for a half-life cycle to occur, 30.2 years. Okay, so what I'm going to do is evaluate this whole thing, this 1/2 to the power of this. That is multiplying P. So if I want to get P by itself, I can just divide both sides by this number after I figure it out. So let's do that. So here's Desmos once again. Welcome back. We got 1/2. 1/2 to the power of 432 divided by 30.2, which is this thing. Okay, 4.9169 times 10 to the negative 5. Well, I'm not going to write that down. I guess I could write that down. It's 4.9417 times 10 to the negative 5. That's this. So I need to divide both sides by this thing to get P by itself, right? This whole thing that I wrote out, this scientific notation, is what I'm dividing by. And so I'm going to divide both sides by this. In other words, in Desmos, what I'm going to do is hit enter on this. So I have saved my answer. Oops, come back. There we go. And then I'm going to type in 0.0048 divided by, and then I believe I can just copy and paste this. which is 97.1327. So P equals 97.1327, right? This whole thing right here was everything except for P. And so I divided both sides by it. And so I took 0.0048 divided by that big number and got my initial starting amount. And that's it. All right, moving on. These ones, I think, make a little bit more sense, at least within the context of the class, because you've probably done something like them before. I know we do this in algebra, but we kick it up a little bit when we go to algebra 2. So this one is compound interest. And I'm just going to write out what each part of the equation means, and then we can just plug it in and solve it. Okay, so we have A of t again, which is our amount, equals P. In this case, P stands for principal, which it also kind of does in the half-life equation, but really that just also means starting amount. Okay. This time, though, we are multiplying not by a half, but 1 plus r over k. All right. This r refers to the rate, which is the percentage that you're increasing by each year, the interest rate. Now, what's important is that in our equation, we need to write it as a decimal. They're going to give it to us as a percentage. We need to convert that into a decimal. So divide by 100, right? Percent divide by 100. This k term right here on the bottom of my fraction inside the parentheses stands for compounds. K for compound, obviously. And it's compounds per year. Now, often they're going to give you some fancy word like quarterly to describe that. And you might have to do a little bit of thinking when it comes to that. And then it's to the power of k times t. K is the same in the bottom of the fraction as it is in the exponent. And then t is, of course, time. And that's always measured in years in this case. All right, so let's set up our equation with our all the information that they gave us in the problem. Our amount with respect to time is going to be equal to my starting amount, my principal, which was how much I invested at the beginning, $750, times 1 plus my rate, which is 3.25%. As a decimal, that's move the decimal place 2 to the left, 0.0325. So 0.0325 divided by the compounds per year. Well, it's hidden within this word quarterly. I don't know if you've heard quarterly report or something like that. That means it happens 4 times a year. So our k value is 4 times, end the parentheses, to the power of 4 from this k times t. Now in this case, because I want to solve for 30 years, I'm just going to plug in 30 for t, which means I'm really plugging in 30 for t over here as well. All right, and this thing looks kind of complicated, but if we just plug it into a calculator, it's going to give us our value of our account after 30 years. Now, this isn't a great interest rate, and it's also not a great amount to a deposit, but if you imagine by the time you're, 40-something, how much money you could have? Well, let's see. So let's go right here. We need to type in 750 times 1 plus 0.035 divided by, 325 divided by 4. I need to end the parentheses and then go to the power of 4 times 30. And that in total is $1,980.56. 1980.56. I'll round up to the nearest cent because that's what the bank would do. Hey, nice. So you can almost triple your money if you leave it into a savings account for 30 years and never touch it. You know, you gotta really, when we talk about, if you're interested in how to save better and what you can do, I'd highly recommend Math 107. You might also touch it in pre-calc a little bit, but really where it gets interesting is when you start adding more and more each month, right? You want to have as much money in your account so that when it compounds, you're making more, right? Because that's what this inside of the parentheses is doing. It's just adding more and more interest to your account. Unless you have a loan, in which case you want to pay it off. You want to get rid of it so it compounds less. All right. Well, one of the compound rates, like quarterly that we talked about, was constant compound, right? Continuous compound. And we saw that that equation used the letter E. And so in this population model, we are assuming that the population is growing by a percentage rate each year. However, that is continuously being accounted for, right? People are always born and dying and whatnot, okay? So let's break down what this equation means. We've changed the letter to N, which stands for number of people, I guess. I don't know. N is just a population word. I don't know why, but it is in statistics. It is in math, whatever. N of t, so the number of people with respect to time, is equal to N sub 0, or N naught, times E to the power of RT, right? NERT. In this case, our starting amount is this value right here, which is our starting population. Okay, N sub 0. Anytime you see this sub 0, so a variable but with a 0 underneath it, that just means initial or starting. It doesn't have to do with what you plug in. It's just a name for the variable. We wanted to use N for population here and here, so we specified this was the starting one by putting a 0 underneath it. E, which is our base, the thing that we're raising to a power, is actually just a number, right? It's like 2.72, right? And that came from the limit as we raised up what K was in this formula, right? So if I set K to a really big number and left it as a really big number up here, that whole thing would turn into 2.72. That's where it converges to. So that's kind of interesting. There's a button on your calculator for E, and we'll also just type the letter E into Desmos and it'll give it to us. The R value is once again the rate as a decimal. So they give it to you as a percentage. You need to convert it to a decimal. And then T is just time once again. So let's set it up for this situation. Our N of T, our population, is our initial population in 2022 is 345,000 people. Well, 345,680. And then we multiply it by E. And then we raise E to the power of this percentage as a decimal. Now be careful. This is a very small percentage, but we still have to move this decimal place 2 to the left. And so it's going to be 0.0085. And then what do I plug in for T, huh? Well, if I look, T is always measured in the amount of time that's passed since you started counting. So really, 2022 is T equals 0, right? This is the initial time, right? It was our population that was initial, and so it's the initial time. And so what I plug in for T is how many years after 2022 it is, which in this case, if we're asked for 2030, means that the number for T is 8, because there's 8 years after 2022 to get to 2030, okay? So let's type this into our calculator. I'll hit enter there, and our new formula is 345,680,000 times E to the power of, and then I'm going to do it in parentheses so I make sure I don't mess up, 0.0085 times 8. And hey, we get a really nice answer, 370,003.87. So our value for when time is 8 years old, when T is 8, our value is 370,003. What was it? 003. And I'm just gonna not include that 0.87. I'm just going to round down always, right? We won't include partial amount of people because in my opinion, there's no such thing. All right. Next thing is interesting. This time we have a decreasing rate. Whoa, we have something that's getting smaller over time. Well, in this case, our rate is going to change from going up to going down, which means our yearly rate, the thing we plug in, is no longer 7.5 positive, but 7.5 negative. So let's see what happens. We're going to set up n of t equals our initial population, 1, 1, 3, 2, 4, 6, 5. That's 1,102,465 times e to the power of negative 0.075, right? I still have to convert it to a decimal, but it is negative now. And then my time, well, it started in 2015. What would you predict the population to be this year? Well, the year is 2023. So that's, once again, 8 years. So times 8. All right, let's see what happens here. I'm interested to know. So I'm going to type in, 1,132,465, my initial population, times e to the power of negative 0.075 times 8. Wow, that's actually a lot, right? 7.5% decrease per year for 8 years. That's like nearly half of the value gone away, or half of the people gone away, which I believe. That's an incredibly high, 7.5% is an incredibly high rate of people leaving. Oftentimes, like this number up top, this 0.85 is more accurate. I'll make it big in a second, don't worry about it. I just got to write down this number. 621,509. And then we have 0.96. Should we round up? No, we're not going to round up. Me at the Taco Bell line. All right, 621,509 people. Okay, so that's interesting. So when it goes down, when decreasing, all you have to do is just make the rate negative, right? It's decreasing. And that's a cool thing about E. There's a whole nother formula if you want to do decreasing rate, like rate of change going down for investing, but for population, you just change the number. So that's kind of cool. All right, next up, we have probably the deepest, but also the thing that we've seen the most throughout the year, which is transformations, right? Carnegie loves these transformations. And so I recommend somewhere on your page, I'm going to move my screen down a little bit. If you want to do it in the margins, or if you want to try and find some space, an empty space somewhere, hey, even if you do it on a separate sheet of paper, write this down, right? This is so important. This will be the transformation equation. Transformation equation, which looks like this. So if we have some function f of x, okay, we can transform it by, actually I don't even want to write f of x. If we want to transform an equation, we can do a few things to it. The first thing we can do is throw a letter a out in front. I'll make it blue. A times, so this thing is multiplying, times f of, so this a is multiplying our function. It's a number that changes the concavity. For example, this -3 is doing that here. F of b x, and then we can throw in a minus c. So that's inside the function if you add or subtract something, and then plus d. Okay, so we have a times f of bx minus c, and parentheses plus d. Okay, well, here's what each of those things mean. The a value, the thing out in front, can dilate, right? Dilate / compress. So it can either stretch things out or make them smaller. And then, notably, if negative, it vertically reflects. Okay, so it dilates and compresses, and then it reflects, right? If it's negative, it changes the graph from going up to going down. Okay? This B also dilates, okay? Except for it impacts the input x. We're not going to see any of those in this test, but what it can also do is if this is negative, it horizontally reflects. So left to right. Oh my gosh, I can't spell. If negative, reflect horizontally. Horizontal reflect. Okay. C, notice that C is being subtracted. Well, this is our horizontal shift, left and right. Okay, so horizontal, the fancy word is translation. Horizontal means left to right. However, because this C is being subtracted in the equation and because it's taking away from the input, this is the one that's weird. So when you add something is actually when you're going left. Why did I do add in red? I don't know. When you add something, you go left. When you subtract something, you go to the right. So it does the opposite of what you might think, and it is the opposite of what D does, which is the vertical reflection. Sorry, vertical translation. Oh my God, I selected all. Translation. Vertical is up / down, and this one follows the rule. If you add, you go up. If you subtract, you go down. Okay? If you have this, if you understand what each of these things does, you don't even have to worry about B in this case. In fact, we will have to think about B when we get to sine and cosine functions or graphing trig functions. But for right now, if you know what A does, C does, and D does, then you're going to feel fine on this. I know it's going to be complicated. There's going to be a lot to do, but you're going to feel okay. All right, so let me do an example. And so in Desmos, they say graph the function 2 to the power x and this transformed function. So let's do that. Let's just follow what they say. Let's go to graphing calculator. This time I'm going to type in 2 to the power of x, and then they want us to type in -3 times 2 to the power of, and then super important in Desmos, if you're going to type in multiple things into an exponent, make sure to use parentheses. So it's x minus 1, and then outside of everything, plus 4. And so there is my graph. Why does Desmos look so blurry? Interesting. Can I refresh? Does Desmos look blurry? I guess it doesn't really look too bad. And that's this, right? So we have our original function, which is this red one here. And then we have our transformed function, which is this blue one here, okay? Well, they want us to sketch it. And so here's how I would do that. I would find some nice points along my curve here. So like that's a nice point, -1, 0.5, 0, 1, and then maybe, I don't know, 2, 4. Those are nice points. I can kind of sketch my graph from there. And so let's do that. I'm at, did my pen break? Oh, there we go. I'll do my red graph as original. So we started at -1.5, 0, 1, and then 2, 4, and then 4, 16. So it's way up here. 3 would be at 9 because it's 2 to the power x. Oh, wait, no, 2 to the power 3 would be 8. That's right there. Okay. So 2 to the power 8 is right there, which means my equation looks like this. Okay. My transformed one, well, it went like this. There was a negative sign out in front, which means it reflects. There was a 3 in front, which means it's going to dilate by a factor of 3. I'll do it here. Dilate by a factor of 3, meaning every point is 3 times what it was before. Inside my function, which is up top in this case, in the exponent, something subtracting x, I need to shift right 1, right? So right 1 because I'm adding in C, and then plus 4 means up 4, okay? Well, what that does is it creates this graph, the one that we had in Desmos, like this. And so I want to find some nice points on this one. First of all, it's heading downwards now. That's because of the reflection. Let's see where the y-intercept is. Looks to be at 0, 2.5. So let me plot this. I'll make it look nicer in a second. Don't worry about it. Or I'll make it big in a second. So 0, 2.5 is like there. I know I have a point right about here. And I have this asymptote that's kind of going off this way. My x-intercept is like 1.4, 0. Let's give it like that. And to be honest, I don't know if I can include 5 points on my graph, so we'll just include these ones. We'll draw it like this. Something like that, okay? So those are what you would graph, right? That's what you would plug in or write in, right? You don't have to do it in 2 separate colors. You just need the parent function, the original, and then based on Desmos, find some points, plot those, and then tell me what it does, okay? And now let's talk about domain and range and asymptotes. Okay, so for the original function, which is f of x, my OG, domain, remember, is left to right. So any place that I can go left to right, well, this graph extends infinitely out to the left. And since this thing is in fact heading to the right, infinitely out this way as well. If you give it enough time, it will reach positive infinity in the x. It'll end up over here. And so our domain is all real numbers, right? In other words, our domain, which doesn't change for g of x, as you notice, because I can go anywhere to the left and also anywhere to the right, believe it or not. Even though it's very steep, it will actually keep going this way. My graph doesn't look so amazing for that, but that's okay, right? It will never completely go up and down. It'll be more like that. So that's also the same as negative infinity to infinity, right? These two are the same thing, all real numbers. This is the interval notation for that. Okay, for the range, we do get stopped. We have some restrictions. In our original function, there's a place that I can't go below, right? There's a lowest point. This asymptote on the x-axis at y equals 0, right? These functions, exponential functions, can never have an output of something less than 0, right, 2 to the power x, because there's nothing I can raise 2 to the power of to get it to be 0, right? And so there's an asymptote at y equals 0, which means the range goes from its lowest point, 0, to its highest point, which it can certainly go up forever, right? This line is pointing up, which means it can certainly hit positive infinity in the y, okay? What's going to change, though, is because I reflected it and I shifted it around, I shifted it up, I now have a new vertical asymptote, right? The place where my line sort of gets really, really close to but never will quite approach is now shifted up 4. So based on my transformation up 4, my new asymptote is at y equals 4. And in this case, that's actually my highest point, right? That's the highest point I can get to. I can get to everything below it, which means my range would not be 0 to infinity, but in fact, negative infinity all the way up to 4. Okay? So what's going to change about this problem is that you're graphing the log, okay? So let me show you in Desmos how to get the log, because it is a little complicated, but I'm going to let you do this one on your own, and then I'm going to give you some notes for the last one. Okay, so if you want a log, you're going to have to open up, well, actually, you might be able to type in log and then hit 2 of 32. Oh, that actually works. Okay, so a couple different options. Number one, let me zoom into this. You can hit this thing, the little bring up the keypad. On your phone, this is what you have to do, and then hit functions. And then if you scroll all the way down to the bottom of functions, or near the bottom, like this way, you'll see this log base A. So log with a little a, you can click that, and then it allows you to type in the base that you want. Or if you're just typing, you can just type the letters LOG. So if you're doing this on a computer. And then if you hit shift and then dash, so underscore, right? The button that's next to 0 and next to plus on your keyboard, in between those, the underscore button, that gives you the subscript, which you can just type 2 and then type x, and there's your to the power x function right there. Okay. What's going to change with this is similar type of transformations, but your domain and range will be different. Okay. And then let me give you some notes on this. So this is the last thing we covered. And you do have to graph the transform and inverse function, but all you have to do is really figure out the equation and plug those in. You just have to sketch it. Okay. But here's what I want to show you. So what we talked about today is that when you take the inverse of a log, or sorry, the inverse of an exponential, so like problem 7 going into problem 8, these two functions are inverses, right? The log and exponents are opposites of each other. However, what's weird about them is that they reflect across this diagonal that goes straight across the graph, the line y equals x if you like, and they will always reflect over this point, okay? So if I move this line around, this original exponent, well, my inverted function will also move. It'll be mirrored, right? Ooh. Like this. Let me try again. I'm just going to do a demonstration, but I keep hitting the side button on my tablet pen, which selects all. Okay, so here's my two functions, right? Fire and ice, I guess. If I take this, my original function, and let's say I want to shift it up 4. Okay, so I'm going to go up 1, 2, 3, 4. Okay, I have to adjust this so that it stays the same distance away from my middle axis of symmetry, my axis of reflection. And so if I move this down 4, which might be your first guess, oh, get rid of that. If I move it down 4, it's actually not going to be totally precise. If I go 1, 2, 3, 4, these are super skewed, right? These are not like at the same place, but mirrored. Instead, what you have to do to account for the fact that this is kind of heading in this direction up from the axis, this one, the inverse, as we increased y in our original, that means that we're going to increase x in our inverse. And so what happens is we shift this thing to the right, okay? So let me make a little table. We're going to have your original function, which is f of x. We did this in the book. And then your inverse function, which is f to the negative 1 of x, or often we'll just call it g of x, okay? Well, in this case, I added something to the outside. I shifted it up. So let's say I do f of x plus d, okay? We'll have that just be here. In our f of x graph, that shifts me up. But in my inverse, what ended up happening when I shifted up is I shifted to the right. Okay. Well, what would happen if I moved this thing down? It's a good question. So in other words, I took f of x minus d. Well, that would move me down in my original function. And let's see a visual demonstration of that. Let's see what would happen. So if I reset these to their original locations, if I move this thing down, so like 1, 2, 3, 4, okay, this thing has got to be the opposite, like the reflection of this, which means if I need to reflect like this point, that point needs to be over here, which means I need to shift this thing 1, 2, 3, 4 to the left. Right? So up is right, down is left in the inverse. So when you apply this to the original transformation or the original function, its inverse has this effect. Okay, sorry about that. We're missing our last two. If we have f of x, and then we're shifting it around left and right, so f of x minus c, well, what would that be? That would be a transformation to the right. Right? If I'm subtracting something on the inside, that shifts me to the right. So let's go back up to these two graphs. Shoop and shoop. If I shift this thing to the right, like 1, 2, 3, then this thing, to account for that, needs to head up here, right? So when I shift this graph to the right, it's going to send my inverse up, which makes sense, right? These flip-flop. And the same is true for if I shift to the left. If I grab my initial function and move it to the left, f of x plus c, that's going to be to the left. And that's going to mean when I graph my transformation, or sorry, when I graph my inverse, that's going to move me down, okay? So using this table, using what transformation is happening to the original, you can figure out what are the transformations that happen to the inverse. You can then write the equation for it, what would happen. Your original function is going to be 2 to the power x, and your inverse is going to be log base 2 of x, okay? And then you just plot those into Desmos and graph it, all right? I'll let you do the last two transformation ones. Good luck. If you have any questions, let me know, and have a good day. But really, this is the important thing, okay? Anyway, good luck.